So we're going to talk a bit today about capacity management for stateful systems. This will encompass kind of our learnings that we've had over many years of managing massive scale storage systems at Microsoft. All right, so let's start with why this is important. First, your customer experience is directly affected by capacity. For example, if your disks are full, you may see significant increases in write latency. Capacity issues can also sneak up on you and cause significant toil for your teams. This may even impact the business itself. If you mismanage capacity, you have to purchase more than you need, or it might prevent customers from using more of the service. It's important to be proactive about capacity issues rather than reactive, so you can give your customers a better experience, save yourself stress, and cut costs. The first step is to get to know your system by getting some data. This includes identifying all your physical and logical limits for each of the different applications and hardware types that you have. For each of these limits, you can then identify the soft and hard limits that you need in place to prevent problems from occurring. It's important to reassess these occasionally for different hardware or for software changes that regress or even improve efficiency. And if possible, it's best to kind of assess this every time that you deploy your software so you can quickly identify and follow up on any issues that might have occurred. Monitoring is an incredibly important part of capacity management. You should think about this not only as your usage, but also the efficiency that you're getting from your resources. There's kind of three main approaches that we use for and consider for monitoring. The first is you need a time series dashboard with each of your limits. Time series databases work great for this, but you can do it with more hobbled together solutions as well. You should have threshold alerts to inform you before you get into a dangerous spot. These are necessary, but don't really protect you from unexpected fast growth. This is where trend alerts are really helpful. We think of this as kind of the time until you reach X capacity, and these are kind of our early warning system. You can implement these similar to how you would implement your capacity forecast and work well if they're aligned with the capacity forecasting. It's even better if you can do this with confidence intervals. So you kind of understand what you expect to happen based on historical trending and seasonality for your applications and services. Let's talk about for efficiency for a minute. At scale, this is one of the biggest methods for cost reductions, but it can also be an approach you can use to avoid a capacity crisis. We typically look for deviations in metrics, either positive or negative over time. And it's important not just to understand the regressions that you might have, but also why a metric might improve to ensure that that change and improvement is a durable change and something that's not going to regress because of something that changed momentarily in the system. It's also important helpful to integrate kind of your change management system to know when a specific deployment or configuration change may have affected capacity or efficiency, so you know that it was attributed towards this issue, not some other issue that might have occurred as well. Try to keep your metrics really simple, but if you do need to use complex or calculated metrics, consider using counter metrics or tension metrics to catch issues with them. In the past, we've experienced issues with data quality for calculated metrics, in which when they were poor, we had issues that might have resulted in a crisis if we hadn't had those counter metrics in place. Lastly, it's important to note that efficiency is not always linear. It may be sublinear as your services receive more load, and you should understand what it looks like when your service is lowly loaded versus a high loaded service. From the limits that you identified earlier, choose the ones that are most appropriately indicate your usage, and use these to forecast your future usage. This doesn't have to be every limit that you identified earlier, but it can help to have a simple forecast for each of them so you kind of understand what to expect over time. In general, even linear forecasting is better than nothing, but you can usually do a model with like a REMA or something else like that, an R for most applications relatively simply. But it's usually better to start with simple models because with more complicated models, you'll usually have less accuracy, and you don't have any basis to compare with, and you'll likely end up with something where you either over-purchased capacity or under-purchased capacity. For the terms, we usually think of short term as kind of the next month, medium term is the next 6 months, and then long term is 2 to 5 years, but it really varies depending on the resource. For example, data centers, for example, take a little bit longer to build than servers. So we usually use something like a 5-year forecast for data centers versus a 2-year forecast for our long-term forecast for servers. There's several important pieces to consider in here as well. One is seasonality, as well as new features and marketing promotions. It's important to really work with your other teams across the organization, not just the technical side, so that you can understand what to expect when marketing decides that they're going to go give away a bunch of new services and capacity, and that doesn't catch you by surprise. You should also expect that you will get new hardware over time, and it may be more capable or even less capable in some cases if you move to maybe more efficient SKUs that have slower processors but are much more energy efficient. You might even find variances in different hardware components, and particularly across different vendors or in versions of the hardware. This is really useful when determining how much of a capacity to purchase. And so we would normalize those and understand what SKU 1 looks like compared to SKU 2 and what the capabilities are of those. Especially when you start off, your forecast will likely be wrong. And so it's really important that you validate those things over time and don't just expect that it's always going to remain the same. It's also important to plan ahead. So when you keep track of your decommission, when you need to decommission hardware, or how long it takes to get new data center or even servers. So depending on your scenario, it may take time to obtain, install, and set up new hardware. Here's an example of what you might need to do to obtain capacity. It's important that you map this out for your own service and understand what each of those boxes are. It's probably going to be a little bit different. Throughout the process, you could experience issues at any point in those areas, and so it's important to have some reasonable buffer in place to avoid you running out of capacity before you're able to install and get it set up. And if it's frequent, this is a good place to look at and understand why that one bar would be longer than another, and if it's something you can tighten up and pull in. So at some point in running a service, you likely will experience an unexpected event, and it's important to prepare for these things in advance. Let's walk through a couple of examples. So in 2011, there were 2 devastating events which disrupted the supply chain generally and globally. One was the Tohoku earthquake in Japan, and the second was flooding in Thailand. The flooding in Thailand is interesting because of a large amount of global hard drive manufacturing and assembly and parts are created and manufactured there. This really disproportionately affected businesses at the time who relied on just-in-time capacity and generally affected the supply chain for about 2 quarters and dramatically increased prices during that time. Would you have been okay if you had reduced shipments of hard drives or a dramatically increased price during this time? Would that have affected your business negatively? And if so, that's an important thing to consider as you go through this. Your assets could get stuck in customs or damaged in transport from the manufacturer, or you could have a batch of hardware that begins to fail faster than you expect and faster than you can get or replace the parts. And most importantly, if you do run out of capacity, can you recover? Does your service get into a wedge state, or does it cause cascading failures across your infrastructure? Think about this kind of as if your root partition were to run out of space. Test it to see what happens, and see how you would recover and go through that process. Don't wait until it happens to understand that. So within our organization, we have a concept of levers. We use these during kind of unexpected capacity issues as methods to kind of preload the things that we want to work on and do as part of the capacity crisis. These are actions that are identified and discussed ahead of time. We implement them as playbooks, and they're frequently tested. They're not something that we just wait until the last minute to use. It's important to discuss the cost of these. So the difference kind of from a lot of playbooks is that there's a cost associated with each of these. There's a benefit, there's a cost. It might be something where you're trading a resource that you have, say like CPU, for a resource that you need, like disk. Not all of these will be technical solutions. It's important that you also look at non-technical solutions like working with sales or marketing to lessen incentives or advertising that they might be giving to customers. Those are also huge levers that you can use in terms of lessening usage so you can make it through until you do get new capacity in place. And many of these are just really specific to your business and applications. So just like your failover policies, it's really important that these, as much as possible, be part of how your business runs and not something that you only attempt to use during a crisis. So let's run through a quick example. Let's say that we had a couch run out of capacity due to incorrect orientation. So luckily, we've considered the situation ahead of time, and we can avoid a person injuring themselves or consider the loss of floor space to correct this issue. Your playbook might look a little bit like this if you were to do that. It's rare that a team would manage their capacity from end to end without any other interaction with any other teams or people. To ensure the capacity management moves smoothly, we have virtual teams in place who work from common data sets towards common goals. We assign accountability areas to each team member and sync regularly to ensure there's no gaps that are falling between the cracks. In general, the product engineering teams are accountable for software efficiency, and in some cases, they're responsible for testing some of the new SKUs. They also are aware of what new features will drive utilization, so they're a really important partner as part of this process. Our hardware engineering team is important to understand what SKUs will be capable of and how this may affect purchases in the near future or in the immediate future. We have a team who specializes in capacity planning, and they're accountable for things like forecasts and data center space allocations. Much of this team is constructed of data scientists and who build the models and make the recommendations based on organic and the non-organic usage that we have. They also work with the marketing team on customer incentives and advertisements that drive increased usage, and with the sales team on large non-organic usage. As SRE, we're accountable for kind of the playbooks, the monitoring, automation, and response if it's needed. Luckily, we don't have a lot of that anymore. But lastly, the V team works really closely with finance to ensure that the capacity plan is cost-effective and reasonable. So let's jump back to levers for a minute. So in some cases, the capability you need doesn't exist yet. So I'm going to run through an example of how we built a lever. We had a problem with high toil due to a rapid growth that we were experiencing. So we set a goal to reduce this and identified a solution. We would automate the migration of capacity between different clusters. We had about 7 different metrics that we were tracking and needed to balance all of them across the various clusters. And given our scale, it would have been really difficult to do this by hand, and particularly with the number of capacity metrics we needed to consider. So we chose to use vector bin packing to solve this problem because we wanted to use something that was predictable, reproducible, and worked well with many dimensions. Doing placement with just one dimension is actually an NP-hard problem, and we knew we needed to do this with about 7 dimensions, many thousands of objects, and many potential destinations. At a high level, vector bin packing works by calculating the dot product of all dimensions of a proposed placement before as well as after it were to occur. In the example in the corner, you can see the movement change and the calculated distance from the original to the new placement for the source and destination clusters. We first attempt to allocate candidates that provide the largest benefit for both the source as well as the destination, and do this until all the objects are placed or all the clusters within the target range. So let's go through a little more detail. So at a high level, it works like this. We first group clusters into sets and normalize each type of capacity, and then aggregate for an overall usage metric. In this example, for each SKU, we've normalized transactions per second for an overall 23% usage. We're clearly imbalanced on transactions per second because we have one cluster as high as 98% and another as low as 4%. So we then determine the target ranges. We typically do this on a sliding scale, and as overall utilization increases, we aggressively balance usage. We do this for a couple of reasons. One is this ensures we have similar amounts of runway across clusters if something unexpected does happen. It also ensures that we're always testing and validating that the functionality works. It's not something that we're just using when we hit this 95 or 98 or 100% type range. So based on our example utilization, our upper range for our utilization is about 55%. So any clusters above this limit would be considered a source, and we try to move them back into that target range. So for each source, we identify the candidates to move and calculate the change in capacity if this was removed from the source and added to the destination. Last, we allocate candidates using vector bin packing, adjusting the simulated capacity with each successful placement. So in this example, we actually don't move candidate 2 because candidate 1 and candidate 3 were sufficient to bring all clusters within our target range. One important concept in the model is constraints. These allow us to specify upper and lower bounds or other criteria that might prevent dangerous placement decisions. For example, we constrain the number of candidates that can be allocated to a specific source or destination, or we might restrict a candidate based on its metrics. We run into a few challenges we needed to solve while designing our solution. So if clusters have an excess of one resource and not enough of another, you need to both add units and remove them. If it's too imbalanced, you can deadlock and not make progress due to the previous safety constraints. Secondly, it can take hours or days for migrations to complete, and cluster capacity can change during this time. We need to avoid overloading a cluster, and also aborting progress as this just wastes resources. Lastly, we need to be judicious in choosing candidates if there's a cost associated with the migration, and we want to make sure that what we're moving is worth the cost. So while we do balancing with about 7 dimensions, we're going to go through a quick example of how this works with just 2 dimensions. It's kind of difficult to do 7 dimensions on paper. We start by putting the clusters on a plane according to their usage. So each of those blue dots represents an individual cluster. And we establish our hard and soft limits that we'd like to keep that usage within. We then identify the weighted usage midpoint and an acceptable range we want to keep the clusters within. The size of the box is determined by the overall usage on each axis. And so it might be skewed one way or another depending on which one has more usage within the given group of clusters. So our goal is to move all of those blue dots into the box. Unfortunately, this isn't always possible directly because resource usage is always positive. And so clusters can only move up and right when adding resources or down and left when removing them. For this reason, we need to both add and remove capacity from upper left and lower right clusters, resulting in zigzag movements towards the target. So this is kind of confusing, so I'm going to step back and do this again in a little more simple example. Because our unit of movement always has positive resource usage for both dimensions, there's only two possible directions. We can both increase both disk and CPU or decrease both. We can't increase CPU and decrease disk. In this case, we want to move towards a new point. However, there's no direct way to do this because we can only add or remove capacity. So we have to move indirectly towards the target by both removing and adding capacity in different steps. Let's go back to our original model for a minute. So as we move resources between clusters, the capacity shifts in the desired direction with some variance due to other resource usage. And when we add new, more capable clusters, the target will adjust the new weighted usage. And we'll schedule migrations to move clusters towards that new midpoint. So let's go back to our original goal for a minute. We wanted to reduce toil and improve scalability. In the end, we ended up actually doing a lot better. Our customer experience improved. We saved the company significant costs by creating more sellable capacity and not needing to purchase new capacity as soon. And we improved our ability to respond to capacity issues by keeping capacity really similar across the different clusters. This allows more time to respond to issues if they do arise. And we met our original goals of reducing toil and improving scalability. So we actually ended up doing much better than we kind of expected. So to kind of summarize, there's a variety of tasks you need to undertake when thinking about capacity management. It's important to proactively decide what is important for your service and implement them as needed. If you have limited resources, you might have to choose. And so monitoring and forecasting are usually some of the most important things and good starting points for most services.